Okay, so if you were watching carefully, you may have noticed that I did something that looks wrong. You should you should definitely we should definitely talk a bit more. So let me point out what the subtlety is, and then let's discuss why it's actually okay. So look at the last boxed equation on the page. What this last boxed equation tells you is if you've got a tensor in one frame, then what is the value of that same tensor in another frame? Okay, good. Now, this transformation rule is something that's true for any tensor. So in particular, if I was to, let's change color. If I was to study the Minkowski metric, if I move to some other frame, so eta prime to mu nu, this would be lambda mu, let's say alpha, lambda mu, let's say beta, eta alpha beta. So the Minkowski metric itself should also change. Now, the thing that I did that may have made some of you feel a bit uneasy is when we were inside the prime frame over here, and I wanted to lower the index of x primed, I still used the Minkowski metric. So what I've outlined in blue there. Well, that's wrong. I should have used eta prime. How come this works? Well, the reason why it works is that if you go ahead and you work out what is eta prime mu nu, the remarkable thing that you'll find is that it's actually equal to eta mu nu. If I consider the full set of boosts and rotations, and I also allow myself time reversal symmetry, so I can change t into minus t, leaving the positions fixed, and I allow myself parity, so I leave t unchanged, but I change x to minus x, y to minus y, and z to minus z, then it turns out that the metric tensor, the Minkowski metric, is the only invariant tensor. Okay, so eta mu nu is an invariant tensor. And what this means is it is the same in any Lorentz frame. And it's the unique tensor with that property. So it's the only invariant tensor. Okay? So the Minkowski metric looks the same in any inertial frame. In fact, you can take this equation that I've just outlined in blue as the definition of the Lorentz group. And you can ask, what are the set of matrices lambda mu alpha that leave the Minkowski metric invariant? And that would be another way in which you could define the Lorentz group. Okay, this equation in blue is so important, I want you to check it, okay? So why don't you check it for a specific example? So what appears there? Well, there's the Minkowski metric. You know what the Minkowski metric is. Here it is sitting over here. It's just a diagonal matrix with 1 minus 1 minus 1 minus 1 along the diagonal. And for lambda, why don't you use this boost along the x direction? You could choose to use a boost along y or a boost along z or maybe some rotation. So you can pick other lambdas if you want, but certainly you know an example of a lambda. I'm sure you can write down others, and you know what the Minkowski metric is. So if you return to this very important equation outlined in blue, you could, for example, let's just think of some example. You could, for example, study what is eta 0, 0? Well, that should be equal to lambda 0 alpha lambda 0 beta, and we'll have an eta alpha beta. So we've got two sums, a sum over alpha and a sum over beta. Write out those sums. Then you know what the lambdas are, you know what the etas are, and you can check, do you get eta naught naught? So is that true or not? Once you've done that, you could study maybe eta naught 1, which is lambda naught. Sorry, let me just. Which is lambda naught alpha, lambda 1 beta, eta alpha beta. Is that true? And you can go ahead and verify that for all elements of the Minkowski metric, and really check that this equation outlined in blue is a correct equation. So with that statement, then, it was perfectly fine that we still used the Minkowski metric eta alpha beta to lower an index in the primed frame. That was no problem at all. Okay, so that brings us to the end of what I wanted to say about the algebra of 4 vectors. So practice this, try to write down as many equations as you can, see which ones are sensible, which ones are not sensible, see if you can check various equations, and you'll get the hang of it. All it takes is a bit of practice. So we're going to leave 4-vector algebra now, tensor algebra, and we want to start now talking about how do we integrate in a Lorentz invariant way. That's something that we're going to have to do. So how do we integrate in a Lorentz invariant way?